Hey everybody, this video is going to cover the lab techniques and tips for lab number 1, chromatography. Now I'm not going to explain every single step of this lab, but I'm going to give you a couple of things that you can use to help you speed things up and give you more context going into the lab to help you with the lab. You're going to be given 12 strips of paper, all approximately 3 to 4 inches long. You need to prepare the strips very carefully before you do the experiment, and if you screw any of this up, you'll have to redo the strip over again. Now the first thing you want to do is make sure you label the strip, and the procedure talks about labeling it with a letter. I'll label this one letter A. You will write down in your data table what A means when it comes to combination of ink, analate, and mobile phase, the solvent. Now it's important that you label on the top of the strip. You're not going to label on the bottom of the strip because you don't want the label itself to mess up your analate, which you are going to be drying on in a few minutes. Another note is make sure you label in pencil, not ink. I'll explain why this is important later. Next up, you are going to use a pencil to draw a line on the bottom of each paper as straight as possible, and you will receive a ruler or a straight edge in order to do this. Also, make sure that this is done in pencil. This line you just drew is going to be your starting line for your analate and will be the line that you use to reference all of your measurements going forward. Next up, it's time to draw on the analate, and that analate is either going to be a Sharpie or a Vis-a-Vis pen, which is a whiteboard marker type pen. You're going to be given black and green, and you're going to be analyzing them in 3 different solvents. Now put 1 dot of ink right on the line that you just drew in pencil. Once again, that's ink on top of the pencil line. And now for the most part, you're ready to do your experiment. To review, you're going to do 3 things on each strip. Label them, draw a line, both in pencil, and then dot with your desired ink. Now it's time to go ahead and get your strip wet. You're going to use a paper clip and unfold it. As you can see right here, you're looking at it from the end, but you're going to unfold it so it's a stick that sits straight across the beaker. And you're going to skewer your piece of paper through the strip and then let the strip hang free over the top of the beaker. Now the first thing I want to point out is you want to skewer it high enough on the paper so that the paper is suspended off the bottom of the beaker. You want a little bit of room underneath the piece of paper between the bottom of the beaker and the paper. This might get a little tricky, and you might have to skewer your paper a couple of times, as you see I have right here. Now, there's enough room on the skewer to actually put 2 pieces of paper per paper clip, but it's important that you never let the strips touch one another while the experiment is running. And the reason being is that when the strips touch, they transfer their inks between the paper. You want to keep the ink on the paper that it started on. Another thing you want to try to avoid is don't let the strips touch the sides of the beaker. This may cause the ink to bleed onto the glass, then back onto the paper, and you won't get a very precise reading. I highly recommend that you set up your paper clips and your paper strips in an empty, dry beaker before you add liquid to it. This will save you any potential redos of the lab. I would also do this for all 3 beakers before you put any liquid in any of the beakers. So in summary, before you add liquid to the beaker, you want to make sure and check for the paper to be suspended off the bottom, that you would have 2 strips and they're not touching, and the strips aren't touching the sides of the beaker either. The strips are a little bit curved because they come from a roll of paper, so you might want to take some time to try and flatten them out as best you can. Now it's time to start the experiment. I recommend taking the strips out, adding the desired solvent in the bottom of the cup, and then putting the strips back in carefully but quickly. When deciding to figure out how much solvent to put into the bottom of the cup, I recommend that you put in just a little bit. You want to make sure that the solvent, which I will represent in blue, starts below the line that you drew on your paper. Giving it enough time to actually begin to creep up using capillary action and meet the line with the ink on it. An improper technique would in fact start the liquid level above the line, and that would be a problem. So you drop the tip of the paper into the solvent, and the solvent begins to creep up through the paper using capillary action. And when the solvent meets the ink, what you may observe is that the ink and the solvent begin to mix with each other, and the ink travels up the strip with the solvent. And in some cases, the ink may separate into different dyes. Now, in other cases, you might witness the solvent go up through capillary action and the ink stays right on the line and doesn't budge an inch. Or centimeter, because this is the metric system. Either way, both outcomes are useful information. In summary, you want to set up the strips dry, take them out of the beaker, add the solvent, put the strips back in carefully, and then, in one specific case, that is the case of hexane, you need to make sure that you cover the hexane beaker with a watch glass. Hexane is so volatile that if it's not covered, the hexane will begin to evaporate off of the paper before it actually travels up to its maximum height. And that's a problem because if it's not in its liquid form, it's not mixing with the ink. Now this adds a level of complexity to the hexane beakers because the beaker will be covered by a watch glass, and there's also little strips of paper sticking out the top and a paper clip little edge that you need to be aware of. And so oftentimes the most common mistake is I see people happen to drop their strips into the beaker of hexane and then they ruin their strips and they'll have to do those particular trials over again. Furthermore, the watch glass tends to fall off or slide off, so make sure someone stays there and holds it on carefully or watches it very carefully so it doesn't fall off and break. Now once you've decided that the solvent is no longer moving up the strip or it's moving so slowly that you can't tell if it's moving any longer, you can stop the experiment. What you want to do at this time is actually take your pencil again and draw a line at the front or the head of the solvent line. Now that solvent line may also be the same line that the ink traveled because the ink is traveling at the same speed that the solvent is, and that's okay. Just simply draw a line on your page as best you can with a piece of with a pencil and mark that head, that solvent front head. This will be useful because the solvents may evaporate, so you won't know exactly how far they travel, but the pencil line will tell you. Finally, it's time to analyze your results. The calculations and analysis in this lab depend on you being able to calculate something known as an RF value, or retardation factor. Now in order to calculate the RF value, you simply need to take the distance the dye traveled in centimeters and divide it by the distance the solvent traveled, also in centimeters, which is why you will receive a ruler in order to do this part. So next let's pretend that your dye traveled starting at the starting line and ended right here, and then your solvent happened to actually end a little bit further than that. So there's two measurements to take. The first one is how far did the dye travel? Start your measurement from the starting line and end it where the dye stopped. The second measurement that you want to do is the total distance the solvent traveled. Now to calculate the RF value, you simply take the distance the dye traveled divided by the distance the total solvent traveled. And that number will probably be a number less than 1. In fact, the maximum number you could get is 1. That is assuming that the solvent and dye traveled the exact same distance. Now if the dye didn't move off the starting line, then the distance the dye traveled is 0, and you divide by the number of centimeters that the solvent traveled, which could be any number, but 0 divided by anything is 0. So in that case, your RF value may be 0. So in summary, your RF value is a calculation of how far the distance the dye traveled divided by the distance the solvent traveled. That number will vary anywhere between 0 all the way up to 1 and any number in between. That takes care of this tips and techniques video for lab number 1. Thanks for listening.